Start the recording. All right. So let's start talking about Gauss's law. So just real quick, think to yourself, what exactly is Gauss's law? Can anyone sort of try to give me their best interpretation of what Gauss's law in your own words? What exactly is Gauss's law?
Wait, is this the same thing we did yesterday?
It's more Gauss's law stuff. It is not the same, but it's similar. It's more practice. Because honestly, that's what you guys need. Is like, because honestly, you can't just do like one day of practice problems and stuff and be good on this stuff.
Okay.
But so it's more Gauss's law stuff. So what exactly is Gauss's law?
It says like the charge inside the closed area is like it's independent of like the volume.
Sort of. That's one way you can apply it. So Gauss's law.
Another application of it would be to find the electric flux, right?
Exactly. Well, so Gauss's law uses the electric flux, which, by the way, what is electric flux? What is this sigma or phi or whatever it is? I don't know. Phi E.
I think it's the number of electric field lines that are piercing through or coming out of the surface.
Mm-hmm. And so mathematically, what would that be? Hint, it's in your formula sheet. Hello, Unit 8.
Yeah, an integral of...
Yep.
Oh, you just wanted the the actual equation. Oh, okay.
Yeah.
Yeah, it's just integral E dot dA.
Yep, so it's this whatever closed surface integral, whatever that is. You guys don't need to understand exactly what surface integrals are, because every example you'll use this for this class, it ends up simplifying. But so it's the closed surface integral of E dot product with dA, which is the area vector of the surface. And then Gauss's law says that this electric flux, this integral of E dot dA is equal to what?
Q enclosed over epsilon naught.
Exactly. So Q enclosed over epsilon naught. So the enclosed charge inside some sort of surface over epsilon naught. Now, what sort of situations does Gauss's law apply to? It has to be a special type of situation.
Are you looking for the answer as it being enclosed?
Not specifically enclosed, because you could have, this box here, and if you have a charge up here in the corner, it's an enclosed surface with a charge inside. But Gauss's law isn't really useful for this situation.
It has to be symmetrical. Right?
Exactly. We're looking for symmetry. Then what are our three types of symmetry we'll see in this class? There's three types of symmetry you can use Gauss's law with.
They're cylindrical.
Yep, they're cylindrical. With a C. Damn it, Dylan. Come on. You only had to retake English 100 once. Cylindrical.
I was here yesterday and I can't remember.
Is it the spherical?
Spherical, yep.
And planar.
Exactly. Cylindrical, spherical, and planar. So those are our three types of symmetries where we're able to use Gauss's law to calculate electric fields. So let's go ahead and start applying these to some examples. So first of all, you guys know what the electric field a distance r away from a point charge would be, right? It's just Coulomb's law, kq over r squared. But how would we go ahead and derive that using Gauss's law? Let's take 3 minutes, then we'll go over it. So we want to derive the electric field. Say we have a point charge q. We want to derive the electric field the distance r away from it using Gauss's law. We want to go ahead and use Gauss's law to derive our electric field, to essentially derive Coulomb's law, kq over r squared. So, first of all, how do we use Gauss's law to do that? What sort of Gaussian surface are we going to use? Or first of all, what sort of symmetry is this? Is it cylindrical, spherical, or planar symmetry?
Spherical?
Yep. It's going to be spherical symmetry, so we're going to want to draw some sort of a Gaussian surface that is a sphere. So I'm going to go ahead.
I have a question.
Yep, go ahead.
Yeah, why did you say it's cylindrical?
We said it's spherical.
I mean spherical.
Yeah. Because essentially it's just a single point in space, and if we can go outward in any direction, 360 degrees around, in the XY plane, plus the Z plane. I'm trying to see, hold up. I can sort of, let's see, is my webcam can work? Because I can turn on the webcam real quick to sort of try to visualize it. But Discord doesn't like to work a lot of the time. Let's see, is this going to work? Pause champ? No, it's not. Okay. But basically you can sort of imagine that you can look around in literally any direction, turn around 360 degrees, up and down, and any angle in between. And if you're at the center of a sphere, you can go in any direction, and it's the same distance to the edge of the sphere. Does that make sense?
Yeah, that makes sense.
Yep. So we have a point charge, and we're trying to find the the electric field at any distance r away from it in any direction. So we use a sphere. So we have our Gaussian surface. We can sort of imagine an invisible sphere surrounding the point charge, and it has our radius r. So that's our Gaussian surface. So now we know what the enclosed charge is. Q enclosed is just Q. So how do we go ahead and solve this integral? The integral of E dot dA. First of all, how do we get rid of that dot product?
You can bring e to the left of the integral because it's a number.
Can we do that yet? Or do we have to first get rid of the dot product?
Oh, first get rid of dot product.
And how do we do that? Harsha, you want to say something?
Yeah, for the dot product, you would just do E times A, or the magnitude of E times A times the cosine theta.
Yep, exactly. So a dot product of any two vectors is the magnitude of the first one times the magnitude of the second one times the cosine of the angle between them. So what direction is the electric field vector? What direction is the electric field in this example?
It's outward.
Outward, radially outward. So at any point, so right here, it's outward, right here, outward, outward, outward. You get the idea. And what direction is the area vector dA for a sphere?
That's also radially outward and perpendicular to the surface.
Exactly. So for any surface, the area vector dA is going to be perpendicular to the surface. In this case, the sphere perpendicular would be outward. And then we also know it has to be outward because outward is positive, inward would be negative. That's just how we've defined. So our area vector is in the same exact direction as our electric field at every given point. So what's the cosine of the angle between them? Or what's the angle between them?
There is no angle.
There's 0 angle. And what's the cosine of 0?
1.
Exactly. So we just have E times dA. And so then, Ben, you mentioned that we can take E outside the integral and pull it to the left side. Why is that?
Because if you have an integral of a number, you can bring it out.
So what you're saying is the electric field E is constant, right?
Yes.
Yeah, exactly. Our electric field E is going to be constant for our entire surface. Also, if there's anyone joining, if you haven't already signed in with the attendance link in the session text or announcements, if you could do that, that'd be greatly appreciated. So we know that our integral of E dot dA ends up becoming E can come out to the outside, and it's just the integral of dA. Now, what's the integral of, let's say just integral of dx? What is that? What's the integral of dx? 1 dx.
Dx.
What was that?
Would that just be 1? Like an integral?
So the integral of dx is just, you're saying it's 1?
Oh, sorry. Would that just be x instead?
Yeah, it's just x. The integral of dx is just x, right? And then value at the endpoints. So what would be the integral of dA? That would just be the total area, right? So the integral of dA, and remember it's a closed surface integral throughout the entire surface, the integral of dA would just be the area of our entire Gaussian surface, E times A. What would be the area of our surface? First of all, our surface is a sphere, right? What's the area of a sphere? Hint, it's in your formula sheets.
Did you ask for the area of a sphere?
Yes,
Is it like 4 pi r squared?
exactly, 4 pi r squared. Boom. And now we basically have our problem solved. Because now we know that this is equal to Q enclosed, which is just Q over epsilon naught. So then we just solve for E is equal to 1 over 4 pi epsilon naught, pulling those 3 out because we're dividing 4 pi r squared over, and I'm pulling out the 1 over 4 pi epsilon naught times Q over r squared. Is that the same thing as what's in our formula sheet for unit 6, kq over r squared?
Yes.
Yep, exactly. K is equal to 1 over 4 pi epsilon naught. It's just a simplified way of, because essentially when people originally derived electric fields, they were like, I don't want to write 4 pi epsilon naught, 1 over 4 pi epsilon naught in front of everything. I just come up with a new constant k. But yeah, in your formula sheet, they are equivalent. So we've gone ahead and we've derived kq over r squared using Gauss's law. Nice and easy. Does anyone have any questions about this? And also, if we wanted to have vector notation, we'll just say it's in the r hat direction, radially outward. All right. So we've done that for a sphere, for a point charge, and we know our Gaussian surface was a sphere. So now let's go ahead and do another example where instead of a point charge, we're going to have a uniform insulating sphere of charge. So we're going to go ahead and have a sphere of charge with, we know it has a radius. I'm actually going to make it bigger. We're going to have this sphere of charge here. Has a radius A, and its charge density is going to be rho. And that's a charge density per volume. So its charge per unit volume is rho. So we want to go ahead and find what would be the electric field if at a distance r, if r is both less than A or if r is greater than A. First of all, what would it be if r is greater than A? Take like a minute and then we'll talk about it. Hint, it'll be very similar to something we've already done. All right, so if we want to go ahead and find the electric field for R being greater than A, what would it end up being and why? If R is greater than A, what's the enclosed charge within our Gaussian surface?
It would be rho times the volume.
Yep. So our enclosed charge, Q enclosed, would just be rho times our volume. And what's the volume of a sphere? Ben, you trying to say something, or is your mic just messing up?
Volume of sphere is 4/3 pi r cubed.
Exactly. 4/3, let's say rho pi r cubed. In this case, our radius of our sphere, where the charge is A. 4/3 rho pi a cubed. But we'll just keep calling it Q enclosed for now. So then what is our electric field? Is it we can just essentially treat it as if this entire sphere of charge is just a point charge, right? So then our electric field would just be the same thing as down here, except in this case Q, we're going to have it in terms of rho if we wanted to. It's just going to be 1/4 pi epsilon naught Q enclosed over r squared in the r direction, for r being greater than A. So now, what if r were less than A? Let's take like 5-6 minutes and then we'll talk about it. So we want to find the electric field inside our sphere of charge. All right, so we want to go ahead and find the electric field inside our insulating sphere of charge. It's a uniform sphere of charge. So, first of all, where are we going to draw our Gaussian surface for this example?
It's gonna be within the radius A.
Exactly. So I'm going to go ahead and erase that so I have a bit more room to work with. So we're going to go ahead and draw our Gaussian surface inside A. So let's say this is our radius R. We go ahead and draw our Gaussian surface in here. Go ahead and erase this because we don't need it anymore. So our Gaussian surface is a radius R inside A. And we know how to solve our integral of E dot dA, right? It's essentially the same process as over here. You know, E dot dA, which is equal to E times the area of our Gaussian surface, which is E times 4 pi r squared. Right? Everyone on board still? So, but the difference here is we want to know what our enclosed charge is. What's going to be our enclosed charge inside our sphere, inside our Gaussian surface?
Wouldn't it just be rho?
It'd be what?
The same as the other one.
Rho times volume, so 4/3.
Oh, no, just rho, not
Well, that's our charge density, right?
Oh, so wait, what are you asking?
We're asking for the actual enclosed charge.
Oh, I'm not sure.
Isn't it just the charge itself?
What do you mean by the charge itself?
Q.
And we want to know what that Q is. So what are we given here? We're given the charge density rho, and we're given what R is when R is less than A.
It's rho times volume enclosed.
Exactly. And what's our volume enclosed?
4/3 pi r cubed.
Exactly. So it's going to be 4/3 rho pi, and in this case, before our surface was outside our sphere, so our Q enclosed was the volume of our entire sphere, so our enclosed charge was 4/3 rho pi a cubed, which are all constants. In this case, though, our enclosed charge is a function of R, 4/3 rho pi r cubed. So if R were to increase or decrease within the sphere, our enclosed charge would change, whereas outside the sphere, it doesn't change. So then from here, we know that E times A is equal to Q enclosed
Sorry,
over epsilon naught.
for R less than A, right?
Yes, this is for R is less than A.
Can you show me where R less than A is?
So like inside here. So for this example here, for example, if this is R,
Oh, that line is R.
yes.
Okay.
Yeah, we're inside our sphere. So we know that E times the area is equal to Q enclosed over epsilon naught, and we just solve for E. So we have Q enclosed, which is 4/3 rho pi r cubed divided by the area of our Gaussian surface, which is 4 pi r squared, it's a squared, times epsilon naught. Now we go ahead and cancel things out. The 4 pi cancels out, r squared cancels out, so we just have r on the top, and we have rho times r over 3 epsilon naught in the r hat direction. It's crazy, right? We have our electric field that actually starting at 0, if we were to go ahead and plot our electric field as a function of r, it's going to go ahead and actually be a straight line increasing up until a, and then it's going to decrease as a function of r squared. Does anyone have any questions about this? Anyone's a bit lost? Any spots where people sort of don't understand?
Yeah, I'm a bit lost on the D.
On what?
D, like the R.
On which part? You just... Do you understand where we got our enclosed charge from?
You got it from the is it a PV but here in terms of R?
Yeah, so we have our rho, which is our charge density, and we have our volume of our Gaussian surface inside our sphere.
Yeah, I think that's where I was getting confused because I was under the impression that whatever the charge is, it will just be that will be Q enclosed, not not the charge then. Because I guess because we don't have the charge, therefore that's why we're doing the
Yeah.
charge times the volume.
Mm-hmm.
But if there was a charge, let's say Q naught, it would just be Q naught at that point.
Yeah. And we can also solve it in terms of Q naught if you wanted to use like a ratio of R over A, but screw that. That's annoying.
Okay.
But so essentially, yeah, in this example, we only have to worry about the charge that is inside our Gaussian surface, and all this charge outside it, out here, is completely ignored and doesn't matter for calculating our electric field. Because remember, Gauss's law, we only care about the enclosed charge for a symmetrical situation, and all the exterior charge can be ignored.
Well, you have rho in this instance, like drawn in the part that we're quote unquote ignoring.
Yeah, I mean, it's just rho is for the entire thing.
Right.
Yeah.
Okay.
This entire
I was
sphere.
just confused because, like, okay. All right, thank you.
Yeah, that's my bad. The rho is also inside here.
Okay.
Any other questions? All right. So, we've gone ahead and we've tackled our spherical symmetry example. So now, let's go ahead and take a look at a cylindrical symmetry situation. So, we want to go ahead and derive the electric field a distance r away from an infinite line of charge. So we have our infinite line of charge, let's say here. We want to go ahead, let's say this line goes on forever in both directions. We want to go ahead and derive the electric field, say like right here, distance r away. By the way, does anyone know what this would be? Because it's actually in your equation sheet. What's the electric field the distance r away from an infinite line of charge?
It would be 2k lambda over r.
Exactly. 2k lambda over r. But we want to go ahead and actually derive it using Gauss's law. So let's take like 4 minutes and then we'll go over it. So use Gauss's law to derive our 2k lambda over r. All right, so we want to go ahead and derive our electric field for our infinite line of charge using Gauss's law. So what sort of symmetry is this situation? So for our point charge, it was a spherical symmetry. For a line of charge, we have
Would it be cylindrical?
Yep. we have a cylindrical symmetry. So that means our Gaussian surface is going to be a cylinder. And how is our cylinder going to be drawn? Is our cylinder going to be parallel or perpendicular to our line of charge? Go ahead, Nicholas.
Parallel, right?
Yep, we're going to have a
It would
line
be
of charge.
parallel.
Yep, it's going to be parallel to our line of charge, and is our line of charge is going to be through the center of our Gaussian surface, right? So we can go ahead and draw. We have a cylinder. We're going to go ahead and have our two end caps here. So here's our cylinder, and let's say it has a length from one end to the other of L. So we have our Gaussian surface, and first of all, we want to know what's our total enclosed charge inside our Gaussian surface. So we want to know what our Q enclosed is going to be. What's our charge density for our line of charge again?
Lambda equals charge over length.
Exactly. So our charge density, lambda, is a charge per unit length. And how much of our infinite line of charge is enclosed inside our cylinder?
L.
Exactly. A length L of our infinite line of charge is enclosed inside our cylinder. So the Q enclosed is lambda times L. Boom. Nice and easy. So now we want to go ahead and we want to solve our integral E dot dA. Our integral of E dot dA. And it's a closed surface integral. So we need to go ahead and integrate over all the different parts of our cylinder. And those three parts, we'll call them part 1, which is the surrounding shell. And we have part 2 and part 3, which are our end caps. So we have the dot product of E and dA for our enclosing shell and our two end caps of our cylinder. So how do we get rid of some of them? We can actually get rid of 2 of the 3. For 2 of the 3 of them, E dot dA is going to be 0. Which 2?
Number 2 and number 3.
Exactly. Our end caps, E dot dA is going to be 0. Why is that, Matt?
Do they like cancel out?
No. Each one of them is going to be 0.
It's 90 degrees, and cosine of 90 degrees is 0. So when you multiply, you get 0.
Exactly. So our area vectors for our two end caps are to the left and to the right, respectively. And what direction is our electric field? It's always going to be radially outward from our line of charge. So it's always going to be, like, for example, below it, it's going to be straight down. Above it, it's going to be straight up. And it's going to be like into or out of the page. If we want to look at it three-dimensionally, you get the idea. So our end caps, dA vectors, are always going to be perpendicular to our electric field vectors. And as Ben said, cosine of 90 is 0. So they both go away. So we literally just have to solve our integral of E dot dA1. And so what's the dot product? What's the angle between the electric field and dA1 for every point? our electric field is radially outward. What direction is dA1?
It's also outward. There's no angle.
Exactly, 0 angle. So our dot product can go away. And that means, is our electric field constant for a distance r?
Yeah.
Yep, our electric field's constant. So once again, same thing as before. We can go ahead and pull our electric field magnitude out. And it's just the integral of dA1. Which, remember, integral of dA is just the area. E times A1. And so what's the area of the surrounding shell of a cylinder, not including the end caps?
2 pi RL.
Exactly. 2 pi r, the circumference of a circle, times the length of our cylinder L. So now we have everything we need to solve. So we have E times 2 pi RL is equal to Q enclosed, which is lambda L over epsilon naught. L's cancel. We solve for E. E is equal to, we have lambda over 2 pi epsilon naught r. And we remember, what is K in terms of epsilon naught?
Is it 1 over 4 epsilon naught?
1 over 4 pi epsilon naught. But yep.
Pi epsilon.
Yep, so 1 over 4 pi epsilon naught. So 1 over 2 pi epsilon naught, which we have down here, is just 2K, which checks out with what we have from Unit 6 in our formula sheet. Boom. We've gone ahead and we've derived our electric field using Gauss's law. So now, let's go ahead and let's do another example, similar to, where we derived it for our point charge, and then we had our sphere of charge, and we derived the electric field inside it. Let's go ahead and, instead of a infinite line of charge, we're going to have an infinite cylinder of charge. It's a solid cylinder going off infinitely in both directions. And we want to go ahead and find our electric field inside and outside our cylinder. So first of all, what would be our electric field outside the cylinder? It's just going to be the same thing as if it was an infinite line of charge, right? We can just treat the cylinder as an infinite line of charge right through the center. But so what if we have R inside our cylinder? So we have our cylinder, which has a volume charge density of rho. Keep that in mind. So we have a volume charge density of rho. And we want to go ahead and find our electric field. I don't really care about when R is greater than A, because once again, just infinite line of charge. But if R is inside A, so if this is a sideways cross-section for a cylinder, we want to find it where R is less than A. Let's take about 5-6 minutes, then we'll go over it. So we want to go ahead and we want to find our electric field inside our infinite cylinder of charge. So first of all, we can go ahead and draw our Gaussian surface, which is just going to be a little cylinder that is inside it. Let's say we'll have a cylinder, once again, with length L, and it has a radius R. This is a little cross section of our cylinder going off. So what's going to be our total enclosed charge inside our cylinder? What's the total enclosed charge inside our Gaussian surface?
B rho times the volume.
Yep, and what is our volume?
Gonna be pi r squared times L.
Exactly. So we have our volume of our cylinder, which is pi r squared times L. So we have our enclosed charge, and now we solve for our E dot dA, which sort of the same thing applies. We have our two end caps of our Gaussian surface, which for both of those, our electric field is radially outward. So dot product cosine of 90 is 0, goes away. We have just the area of our outer shell along this part of our Gaussian surface. And E dot dA, which is E times the area, which is E times 2 pi RL. So then we just plug everything in. E times 2 pi RL is equal to rho pi r squared L divided by epsilon naught. Dot product of V dot dA is equal to Q enclosed over epsilon naught. Solve for E is equal to, let's see, pi cancels out, L cancels out, 1R cancels out. We can divide the 2 over, and we get rho R over 2 epsilon naught. So once again, we have, if we were to go ahead and graph our electric field as a function of R, it's going to linearly increase until we get to the radius of our cylinder, and then it's going to decrease off as a function of, instead of 1 over r squared as before, it's going to decrease as a function of 1 over r. Does anyone have any questions about this? So once again, it's sort of the same thought process. We want to find our enclosed charge inside our Gaussian surface, and then solve our E dot dA, and we just then algebraically solve for E. Same exact process for every single Gaussian or Gauss's law example you'll see. All right. So let's go ahead and hop into another example. So we've covered spherical symmetry and we've covered cylindrical symmetry. And remember, what's our last type of symmetry? Planar symmetry, exactly. So let's go ahead and let's think about planar symmetry, and let's use it and use Gauss's law to derive the electric field. Let's close off this area up here. So we're going to have an electric field a distance r away from an infinite sheet of charge. So let's say this is our infinite sheet going into and out of the page. It has surface charge density sigma. Now it goes into and out of the page in both directions forever, and then up and down both directions forever. We want to find what our electric field is a distance r away from it. Let's take like 5 minutes, then we'll go over it. All right, so we want to go ahead and derive our electric field a distance r away from our infinite sheet of charge. So it's a planar symmetry situation. So what is our Gaussian surface in this example going to look like? So for our spherical example earlier, our Gaussian surface was a sphere, right? For our cylindrical situation, our Gaussian surface was a cylinder. For our planar situation, what's our Gaussian surface going to look like?
Planar.
Ha! Debated. Nah. It's not another plane. Gotcha. Nah. But so we want to go ahead and draw a Gaussian surface that is 1, symmetrical on both sides of our sheet of charge, and 2, all the surfaces of our Gaussian surface are either parallel or perpendicular to our electric field. So for 1, this at least should be somewhat intuitive. We have an infinite sheet of charge. We know our electric field is going to be exactly away from our infinite sheet of charge on both sides, right? It's going to be perpendicular to our sheet. So we want to draw some sort of a Gaussian surface that is always, all surfaces of it are either parallel or perpendicular to our electric field. So let's start with a surface that is perpendicular to our electric field, or the area vector would be perpendicular. Let's draw one side of our Gaussian surface is going to go through our infinite sheet from one side to the other like this. Does that make sense? And so let's say it's some sort of let's say it has a top surface and it's going to have a bottom surface as well. Say like some sort of like 2 sheets here. And our area vectors for these sheets are upwards and downwards respectively, perpendicular to our electric field. And let's say we also we're going to have these sheets, we're going to sort of turn it into a box where we have our sides of our box, our side that is behind and our side in front. Our area vectors are into the page and out of the page respectively. That's still perpendicular to our electric field, so it still works out. And then the last part of our Gaussian surface, we have the end points of our box where our area vectors are to the right and to the left respectively, which is parallel to our electric field. So it all checks out. We have our Gaussian surface, which is essentially be a rectangular box that is, the left and right sides stretch a distance r from our infinite sheet, and all surfaces of it are parallel or perpendicular to our infinite sheet of charge. Now there's another example, there's another type of Gaussian surface we could use here. I believe, does anyone know from like some of the lecture slides and what Dr. Goolsby Cole uses? he usually likes to draw cylinders, right? Would the cylinder also work? All the surfaces of the cylinder would be parallel or perpendicular to our electric field, right? So if we have our end caps are going to be parallel, and then all the different parts of it, all the other area vectors for our shell are going to be perpendicular. But let's stick with this example up here. So we have our box, distance r out, and let's say our end cap has an area A. So what is our total enclosed charge inside our box? What is the total enclosed charge of our infinite sheet inside our box?
Would it be sigma times the area?
Exactly, sigma times the area. So our Q enclosed is equal to sigma times our area. So now we want to go ahead and solve our E dot dA, our integral of E dot dA. So we have our, let's have our 6 sides of our Gaussian surface. We have side 1, side 2, our 2 end caps. And we have 3, 4, 5, and 6, which are the 4 sides of our box. Which of these E dot dA, E times dA times the cosine of the angle between them, which ones end up being 0? Cosine of 90 is 0, so which area vectors are going to be perpendicular to our electric field? It'd be 3, 4, 5, and 6, right? Go ahead, Matt.
Yeah, since it's going like up and down, it's going the opposite direction of the sphere. So I thought it was like 3, 4, 5.
Yep, exactly. So we have 3, 4, 5, and 6. Our area vectors are like out of the page, straight down, into the page, and straight up, all of which are perpendicular to our electric field, which is straight left and right. So all those end up being 0. So then our closed integral of E dot dA just ends up being the integral of E dot dA1 plus integral of E dot dA2. And once again, we're going to say that dot product is cosine of the angle between. Cosine in this case for both of them is 0. So then E dot dA is just E times dA. So this ends up being E times the integral of dA1 plus the integral of dA2, which the integral of dA is just the area. So we have A1 plus A2, which is just 2A, since A1 and A2 are both big A. Then we just solve for E. We know that this E times 2A is equal to sigma A over epsilon naught. So then E is equal to sigma A over 2A epsilon naught, which is equal to sigma over 2 epsilon naught. Boom. Constant electric field, no matter how far away from our sheet of charge we are. Anyone have any questions about this? All right. Well, in that case, I'm going to go ahead and wrap up the session here. We're slightly over on time. I did have one more example prepped, but I'll probably go ahead and reuse it for a future session. You guys will be doing a whole bunch of Gauss's law practice and a whole bunch of different problems with conductors and insulators over the next week or two. So, thanks for coming, guys. Hope this helped out. Same time next Wednesday and Thursday, 1 o'clock. Have a good day. Good luck on your quizzes tomorrow.